Alright, for today's pre-lecture video, I want to take a closer look at Lenz's law and how we figure out the direction of that induced current. So we start with what we call Faraday's law. And Faraday's law explains why in some situations we will actually see a current flow in a circuit or a coil when there's not a power supply or a battery that's going to make that happen. So we usually refer to the battery as the EMF. So Faraday's law is expressed in terms of the EMF. So we use that script E, and it says it's minus the time rate change of the magnetic flux with respect to time. And so basically it's saying if the magnetic flux is changing over time, there will be an induced EMF. So that's like creating a voltage, and that potential difference can allow current to flow in the circuit or whatever we're taking a look at. Just as a reminder, the magnetic flux is the dot product of the magnetic field and the area. So it looks like BA cosine theta, where theta is the angle between the magnetic field vector and the area vector. Remember, the area vector is perpendicular to the area itself. So if we're thinking about the way that flux can change, we might want to look at this expression one more time. B dot A is our magnetic flux, which is equal to B times A times the cosine of the angle between them. So the types of things that can make the flux change could be a change in the magnetic field, like its magnitude, or it could be a change in the magnitude of the area that the magnetic field is passing through, so that's going to affect the magnetic flux. It could be that the orientation of the area vector with the magnetic field vector changes. So really basically we're talking about all three of these terms here and how each one of those could be changing, and that would cause the change in, that would cause the induced EMF. Also, it could be some combination of all these three things. It doesn't have to be just one. And we're thinking about the changes that happen over time because the EMF is minus d phi dt. So the difficult part about this, really, I think, in terms of talking about Faraday's law, has to do with that negative sign that you see in the expression. That negative sign has everything to do with Lenz's law, because Lenz's law helps us figure out which way the induced current will flow. So we get this change in magnetic flux, which induces an EMF, which allows the current to flow, but of course the current can have two choices in which way it's going to go. It's not a random thing, it actually flows in a very particular way, and that's what Lenz's law talks about. So basically Lenz's law says that the flow of the induced current will oppose the change in magnetic flux, flux, which caused the induced current in the first place. And so let's talk a little bit about how that is going to happen. Because we know that there's some sort of change in flux and that's what's causing the current, and we're being told that our induced current is going to try to oppose that change. So basically what we have to figure out when we're figuring out which way the induced current will flow, there's sort of a series of steps that we go through. So basically first you have to identify if the magnetic flux is increasing or decreasing. Is it getting stronger? Is it getting weaker? And again, remember there's different reasons that can be happening: change in area, change in magnetic field strength, etc. If it is increasing, what happens is you want the induced current to create a magnetic field in the opposite direction to the existing field, because in the end, when we're talking about Lenz's law, the only way that it can actually sort of oppose the change in magnetic flux is that the induced current will create another magnetic field. And so it's always thinking about what will be the direction of the magnetic field that is created by our induced current. So if we have an increasing flux, we want to create a magnetic field in the opposite direction because that's going to tend to work against the increasing flux. That's why the opposite is so important there. However, if it's decreasing, if the flux is going down, you actually want to bolster that flux by creating a magnetic field in the same direction. And so you have to figure out which way your induced current should flow to make that happen. And so you first have to decide, do I want to create a magnetic field in the same direction that there is already an existing field, or in the opposite direction? Once you determine that, you just use the easy right-hand rule and to try different directions for your current and see which direction will create the magnetic field that you want. And that's how Lenzs Law works. If you break it down into a series of steps, it's a lot easier. So let's look at an example. So in this example, we have a bar magnet and it's moving towards this solenoid. And what we're going to try to figure out is, for the solenoid, what will be the induced current in it. And so we're going to draw the magnetic field lines of this bar magnet. Remember that the magnetic field comes out of the north and goes into the south. And in this case, our magnet is moving towards the solenoid. So as we're moving towards the solenoid, the magnetic field that goes through the axis of the solenoid will be increasing. And when I mean increasing in strength, because the reason is because as you get closer to the magnet itself, the field gets stronger. So as that magnet's coming towards the solenoid, the magnetic field passing now through the solenoid due to the bar magnet is getting stronger in strength. And it's also pointing to the right, because we have the south pole of that magnet, and the magnetic field goes into the south pole, so the field that's going through the solenoid is going to the right. And so because of this, the flux through the solenoid is increasing. And so Lenz's law says that we want to create a magnetic field that opposes that increase in the magnetic flux. And so we want to create a magnetic field through the solenoid that's going to point to the left, because that will oppose the change. And so what I'm going to do is I'm going to look at one of these turns of the solenoid, and I'm going to use my right-hand rule to try to figure out which way the magnetic field should go. So the first thing I'll try is if I point my thumb down. So I'm looking at one of these turns that comes in the front of the solenoid, and I'm pointing my thumb down, and I'm curling my fingers, and I'm looking at what my fingers do behind my thumb, and I see that that would create a magnetic field to the right. So if I do a current that points down, will create a magnetic field to the right. And that's not what I want. And so I try a current up again, so I point my thumb up, I'm looking at one of those turns, I'm looking at what my fingers are doing behind my thumb because that's inside the solenoid, and I find that if a current points up, it creates a magnetic field to the left. And that is what I want. And so what I'm going to find is that the current that's induced is going to sort of go up in these turns, and then that also means it will continue around the circuit in the direction that I've shown with the arrows. All right, so that's one test. I'm going to look at the other situation. If the magnet is moving away, and again I'm going to draw the magnetic field lines to remind you what they look like. And they're going to be going into the South Pole over here. And so, as the magnet moves away, we know that the magnetic field through the solenoid is getting weaker. We also know that that B field points to the right. And so to oppose that change, Lenz's law will tell us that we want to create more magnetic field to the right to oppose the change. And so again, now this one becomes a little easier because we've already done this, but if I look at one of these curls, and now I'm going to, if my thumb points down, so if the current is down, and I look at what my fingers are doing behind my thumb, which way are they curling, the magnetic field is to the right, and that's what I want, and so that becomes my choice. And so this time the magnetic field, the current is traveling around in the opposite direction, which we should have predicted because it was the opposite situation, but in any case we can always be practicing to make sure that we can do it on our own and that we'd be able to do it if we were asked. So those are just two simple examples of using Lenz's law, and we will talk about more in class tomorrow.